Black holes are supposed to be one-way doors to oblivion. Nothing, not even light, can escape once it crosses the event horizon. But Stephen Hawking discovered something unsettling in 1974.
They're evaporating. Slowly but inevitably, black holes are leaking away into nothingness. And the reason why rewrites everything we thought we knew about time, space, and the edge of physics itself.
Today, we're breaking down Hawking radiation, the quantum process that kills black holes. By the end, you'll understand why the universe's most fearsome objects are actually temporary, and why their death reveals something profound about how reality works.
First, we need to understand the event horizon, that boundary where gravity becomes so extreme that not even light can outrun it. For decades, physicists assumed the event horizon was truly absolute. Once you're in, you're gone forever.
But Hawking asked an uncomfortable question. What happens at the quantum level, right at the boundary? And that's where things get strange. According to quantum mechanics, empty space isn't really empty.
Virtual particles, electron-positron pairs, or photon pairs, are constantly borrowing energy from the vacuum and paying it back almost instantly. They exist in debt to the uncertainty principle. Normally, they annihilate each other and vanish.
Now place that process right at the event horizon. A virtual pair forms, one particle just inside, one just outside. In normal space, they'd quickly annihilate. But here's the cosmic accident. The black hole's gravity is so intense that it rips them apart before they can recombine.
The particle inside crosses the event horizon and falls into the black hole. The one outside escapes to infinity. But here's the kicker. To escape, it needs to carry away energy, and that energy has to come from somewhere.
It comes from the black hole itself. The escaping particle represents a loss of mass, or more precisely, a loss of gravitational binding energy. The black hole pays for its own radiation by shrinking, infinitesimally but measurably. It's bleeding away.
This is Hawking radiation, and here's where physics gets genuinely weird. Smaller black holes evaporate faster than larger ones. A stellar mass black hole would take longer than the age of the universe to disappear, but a tiny primordial black hole could detonate like a bomb in an instant. Why does size matter like this? Temperature. Smaller black holes have higher surface gravity, which creates stronger tidal forces at the event horizon. This amplifies quantum fluctuations, heating up the radiation. Higher temperature means faster evaporation. It's a feedback loop. As the black hole shrinks, it heats up, radiates faster, and shrinks even more.
Hawking radiation represents something unprecedented in physics, a bridge between two frameworks that normally don't coexist. General relativity governs gravity and spacetime. Quantum mechanics governs particles and probability. Here, at the event horizon, both are essential. Neither alone can explain what happens.
Here's the kicker. We've never directly observed Hawking radiation. For stellar mass black holes, it's far too faint to detect. But if we ever discovered a primordial black hole, we might actually see one exploding in real time as it reaches the end of its evaporation cycle. It would look like a massive gamma ray burst.
Black holes aren't immortal engines of gravity. They're temporary, their final moments encoded in the quantum foam at their edges. And that revelation changed how we think about the ultimate fate of the universe itself.
Subscribe. New science every week.